press the bell icon on the YouTube app and never miss another update.
This is first PUC Physics Oscillation Part 6. In the previous class, that is in Part 5, we have discussed about one of the most important concept, right, that is a phase of a vibrating particle, and how to find the phase of vibrating particle at different instants of time during simple harmonic motion, and how to express it in terms of fraction of time period as well as in terms of fraction of the angle 2 pi, right. And we have also discussed about epoch, right, initial phase. When a particle executing simple harmonic motion is not in mean position or equilibrium position, when time t is equal to 0, then it has some initial displacement and initial angular displacement from the mean position. That initial angular displacement is called initial phase or epoch. In terms of epoch, the equation becomes slightly changed, that is the displacement equation. That becomes y is equal to a sin omega t plus phi naught. And now we are having another concept, that is velocity of simple harmonic motion. The velocity of simple harmonic motion at any instant of time is the time rate of change of displacement of the particle at that instant of time. And remember, velocity v is equal to omega into square root of a square minus y square. This velocity is not constant, it changes with respect to time or displacement. Now at extreme positions, velocity of simple harmonic motion is 0 momentarily, right? And when the particle is at mean position, the velocity is maximum, and maximum velocity v is equal to omega into a, where omega is angular velocity and a is amplitude, right. Now let us discuss another concept, that is the acceleration of simple harmonic motion. Now please. Acceleration of SHM, it is denoted by A, right. It is a vector quantity having both magnitude and direction, and we know that from the characteristics of simple harmonic motion. In a simple harmonic motion, magnitude of acceleration is directly proportional to displacement, and acceleration is always directed towards the mean position. So here, acceleration of a particle executing simple harmonic motion at any instant of time is the time rate of change of velocity of the particle at that instant of time. That is, here acceleration is equal to time rate of change of velocity of the particle executing simple harmonic motion, right. That means the acceleration a, right, is equal to dv by dt, where dv is the small change in velocity of simple harmonic motion and dt is the time taken. This we may take as equation 1, right. But here velocity is the rate of change of displacement, therefore dy by dt. Therefore acceleration is also given by d by dt of dy by dt, right, or acceleration A is equal to d square y by dt square. Let us take it as equation 2. So acceleration is the derivative of velocity with respect to time, and also acceleration is the second order derivative of displacement with respect to time. That means when we differentiate displacement, we get velocity. When we differentiate velocity, we get acceleration. Now we have, right, now we have displacement at any instant of time. Displacement at any instant of time, y is equal to a sin omega t plus phi naught, where phi naught is the initial phase, a general equation. Now it's a velocity at any instant of time, v is equal to, so we have derived that one. So omega a cos omega t plus phi naught, it is the expression for velocity. When we differentiate this y, we get this velocity. Now acceleration, at time t, right, a is equal to, this is dv by dt, that is equal to d by dt of, now what is velocity v? Velocity v is omega a cos omega t plus phi naught. Now we have to differentiate this term, omega a cos omega t plus phi naught. Therefore we have acceleration a is equal to, while differentiating this one, right, the whole thing, we get omega, right, a constant, right. The differentiation of cos theta is minus sin theta, therefore here we get minus, right, sin omega t plus phi naught, right. When we differentiate this term, we will obtain a cos omega t plus phi naught, right. And then when we differentiate omega t, we get omega t. Here a is omega constant, a constant, and phi naught is constant. So when we differentiate this with respect to omega t, we will get omega. Therefore acceleration a is equal to, we take the minus omega into omega square a sin omega t plus phi naught. Let us take it as equation 3, right. In terms of trigonometric function, right, there is harmonic function. Expression for acceleration is a is equal to minus omega square, capital A sin omega t plus phi naught, right. But what is the significance of this negative sign? This indicates that acceleration is always directed towards the mean position, whatever may be the position of the particle from the mean position, but the direction of acceleration is always towards the mean position. But in velocity, we don't have that negative sign. So here velocity have 4 directions. In positive direction, away from mean position, next towards the mean position, in negative side, away from the mean position, and then towards the mean position. But acceleration is always directed towards the mean position, whether the particle position is towards right or it is towards left, that is positive side or negative side. But see, what is this term A sin omega t plus phi naught, that is equal to displacement, right? Therefore, we can write acceleration A is equal to minus omega square y, right? Right, this is equation 4 we can take, right? So, acceleration of a particle executing simple harmonic motion, right, is given by A is equal to omega minus omega square y, right, where omega is constant, right? Now y is displacement, right? Therefore, here this acceleration A is directly proportional to displacement. That is, magnitude of A is proportional to displacement. Now A is proportional to minus y. That indicates acceleration is towards mean position, right? So that means it is a simple harmonic motion. If any particle executing, right, harmonic motion is considered, if we can show that acceleration of that harmonic motion A is equal to minus omega square y, in other words A is proportional to minus y, then that harmonic motion is obviously a simple harmonic motion, right? So to say whether a harmonic motion is a simple harmonic motion, right, we will find the acceleration of the motion. If it is found to be proportional to minus y, where y is displacement, then it is a simple harmonic motion, right? Is it clear? Why I am telling these things is, while deriving an expression for period of oscillation of a loaded pendulum, we are using this concept. We show that the oscillation of the loaded spring is a simple harmonic motion by finding its acceleration, which comes out to be A is equal to minus omega square y. Then we will find that expression for time period. Is it clear? A is equal to minus omega square y, equation 4, right? We have taken it. Now, note we can take. Now we have, right, acceleration A of simple harmonic oscillation. A is equal to minus omega square y. That we have taken equation number 4. But here the significance of negative sign is only to indicate that the direction of acceleration is always towards the mean position. In other words, we can take this as vector A is equal to, right, minus omega square into vector y in the vector form, right? Now here vector y is always directed away from the mean position, whatever may be the, right, position of the particle. When we say that the term displacement, it is the change in position of a particle in a given direction. Displacement has both a magnitude and direction, but it is always directed away from the mean position. The negative sign indicates that direction of acceleration is opposite to the direction of displacement, that is towards the mean position, right? Now when we take magnitude of acceleration, sometimes we need, right, a scalar form of equation and vector form of equations, right? Now physical equations are expressed both in scalar form and vector form, right? It is because some physical quantities are scalar quantities and some physical quantities are vector quantities, right? A quantity which has both magnitude and direction, right, is called a vector quantity, right? It is more correct to say, I think, a quantity having both magnitude and specific direction is called as, right, a vector quantity. The specific direction means in the direction of motion, as we deal in the case of translational motion. And a quantity which is having only magnitude and no direction is called a scalar quantity, right? Now when we take scalars, mass, volume, density, work, energy, power, volume, right, etc. are scalar quantities. They do not have any direction. Whereas the quantities like displacement, velocity, acceleration, force, momentum, electric field, magnetic field, torque, angular quantities, they are all vector quantities. They have both magnitude and direction. When I simply say that it is distance travelled, right, is equal to 5 meter. That's all. Here this has no direction at all, no specific direction. But whenever I say displacement is equal to 5 meter, it is wrong, because it is not the complete information, right? We say from north to south direction or any specific direction, then it will come. So here when I say 5 meter, it represents only distance travelled. When I say 5 meter from, right, north to south, it represents displacement. Here this is magnitude and this is direction. So here when we take the position of the particle from the mean position, we say it is not distance, right? It is the displacement, we call it as, though it is a magnitude is, of course, it is the distance between the position of the particle and the mean position. But we are not saying the distance travelled by the particle. We are saying the distance of the particle, I mean displacement of the particle at any instant of time. It is because it has a direction, right? The direction of displacement is always away from the mean position, whatever may be the position of the particle, right, from the mean position. So acceleration, again a vector quantity, but it has direction towards the mean portion. That is the significance, right? So when I say F is equal to ma, it is a scalar form. Just I needed only the magnitude of force, but not the direction. Direction is there, but direction is not needed at this situation because I need only its magnitude. But when I say that vector F is equal to m into vector A, where mass is a scalar quantity. So here I am considering both magnitude of force and direction. Here this is the scalar form of expression for force according to Newton's second law. It gives only the magnitude. But this is vector form of the same law, right? Vector F is equal to m into vector A, right? Then it is associated with both magnitude and direction. So we are considering both magnitude and direction. Similarly, right, we have distance and displacement. Distance is the scalar form of displacement, right? And speed and velocity, right? Speed is the scalar of the velocity, right? Similarly, when we take magnitude of acceleration, when we are dealing with numerical problems, right, we don't consider the negative side, right? Here A is equal to omega square into y. Where we needed only the value of magnitude because we know that the direction is always towards the mean position, and we can take this as equation 5. This is equation 4 we have in our discussion. Now, here we take a particle executing simple harmonic motion changes its position with respect to time. Generally, we consider 3 positions. One mean position and other 2 extreme position in positive side and negative side. Now, let us see what is the value of acceleration at mean position and at extreme positions. So, at mean position, here MP is the short form used for mean position. At mean position, here we have A is equal to omega square into y. At mean position, what is the value of y? Y is equal to 0. Y is equal to 0. Therefore, right, acceleration is minimum and the minimum acceleration is equal to 0 at mean position. This way may take it as equation 6. Now, at extreme position, both the extreme position towards positive side or negative side. Now, y is equal to A. Again, A is a magnitude of right amplitude which remains the same, right? Therefore, A maximum, right, because the maximum value of displacement is amplitude, so this is equal to omega square into y. This we can take equation 7, right? So we have taken 7 different forms of right equations for acceleration, but most important thing is you have to remember this form of equation, right? Acceleration A is equal to minus omega square y. One of the significance of this equation is that if acceleration of motion of any particle comes out to be A is equal to minus omega square y, or A is equal to minus k into y square, right, where k is constant. In this case, right, this k is equal to, right, omega square, right, proportionality constant, right. We see in physical equation there are so many proportional, right, equations, and they have different proportionality constants, but in all the equations, right, generally the constant is taken to be k. In some special cases the constants may be different, just like 2 pi, right, just like c, the speed of light, etc., Planck's constant h, gravitational constant g, right. Now this k, right, when in equation, either it may represent proportionality constant, it may be different in different equation, right. The k is not the same in all equation, right. Its nature, value, right, and other things may be different from equation to equation, right. So when A comes out to be equal to minus ky square or equal to minus omega square, then that motion must be a simple harmonic motion. Right? Is that clear? Now, let us discuss another concept, that is restoring force, represented by the symbol F, just like any other force. Right. Now, let us consider a simple pendulum. In its mean position, a bob suspended by means of a string. Let M be the mass of the bob, right, which is concentrated at its center of gravity, that is the geometrical center of the spherical bob, right. This is length L of the string. Now, when the simple pendulum is at rest, the simple pendulum is at rest. Now, the position will be at equilibrium position, that is the mean position here. Now, when we consider what are the forces, right, acting on the system, here obviously the weight of the bob is acting vertically downward direction, but still it is hanging in air, not falling down, because it is held by the string, right. Now, the string exert a force on that mass or bob, right, in upward direction, that is generally called as tension in the string, because we know that according to Newton's third law of motion, for every action there is an equal and opposite reaction. So here mg is the action, right, acting on the string, and tension is the reaction acting on the bob. Here the both P and mg are in opposite direction. P minus mg is equal to 0. In other words, magnitude of tension is equal to magnitude of, right, weight of the bob here. So here net force on the system is 0. Therefore, the particle is at rest. It is neither moving in vertical direction nor moving in horizontal direction. Now, we'll take the same case the particle is in mean position, right, is displaced through certain distance. How to produce displacement in the bob? Because by itself it cannot change its position. Only an external unbalanced force can change the position of a body. That we know that it is the one of the basic concepts of mechanics, right? Now, right, when the bob is pulled aside by applying a force. Now let this be new position of the bob, new position of the bob, right? Now I will hold that bob and pulled this aside, right, so that the bob displaces through a distance y. As long as I am holding this bob, the bob will be at rest. Now, this is, we call it as external force, a force that is acting on the system from outside, external force, or we can call it as displacing force, the force that causes displacement in the bob, right? Now here we know that the bob is at rest and the force is acting on it. When I hold here, it is, I am applying the force. That means, right, whenever a force is applied to change its position, right, here a force F comes into play. This force F is called, right, restoring force. This force F is called as restoring force, right, that comes into play. Again, as bob is at rest, F minus F external is equal to 0, right? So there are two forces right now in horizontal direction acting on the bob, right? There are other forces also, but I am taking only those forces which are acting in horizontal direction because it is neither moving towards left nor moving towards right. Now at this stage, so F is equal to F external, right? So magnitude of restoring force is equal to magnitude of, right, external force which displaces the body. As long as the bob is at rest, this is very important, right? There are two forces, right? Now what is the F? It is a reactional force, right? It is F external is, right, F external is one force, right? This is another force F. This restoring force that comes into play, right, because of the change in position, it has a tendency to bring the bob back to its equilibrium position. If I leave that bob, means I have removed the external force. Does the bob remain there? No, it will not remain there. It starts moving towards the mean position, right? Now here when I released the bob, that means F external has made 0. Now this restoring force F, right, at displacement y it brings the bob, right, back to its mean position, right. Now the force on the bob in horizontal direction is this F, right. Now what is the role of this F here? To bring the bob back to its mean position or equilibrium position, right. So what is done by the restoring force? It restores the bob into its mean position, right. Therefore this force is called as restoring force, right. So the force acting on a particle, right, that brings back the particle to its equilibrium position after the removal of, right, external force or displacement force is called restoring force, right. A force acting on a particle, right, that brings back the particle to its mean position or equilibrium position after the removal of external force or displacement force is called as restoring force, right. Now we have the F is the restoring force, right. Here the bob is moving, here figure 1, figure 2, figure 3. In figure 1 bob is at rest in mean position. In figure 2 the bob is at rest at displaced position, and here the bob starts moving towards the mean position under the action of restoring force. And again remember that I am telling you, here I am not considering weight, tension, they are all there, but I am considering only the forces in horizontal directions, right. You got my point. Now in general we can say there are three forces here. One, tension in the string, second one, weight of the bob, and third one is the restoring force. Forget about tension and weight, that we will consider in the next topics, right. Here we are dealing with only horizontal forces, it's right. Now this restoring force, right. So if m is mass of particle and a is acceleration produced in it, right, then according to Newton's laws of motion, an external unbalanced force acting on a body always produces acceleration in it, right. Now the magnitude of force is equal to the product of mass and acceleration. So in this case that restoring force, that F is equal to ma, where m is mass of the particle and a is right acceleration. Now when the particle comes to the mean position, it will not stop there, right. It will not stop there because it has some momentum. Due to that momentum it overshoots the mean position, but it will not stay in any other position away from the mean position. Again it starts moving towards the mean position, right, and began to oscillate here, right. Now this is ma, where a is acceleration. Since the particle is executing simple harmonic motion, right, under the action of restoring force, now this acceleration of simple harmonic motion, right? A is equal to minus omega square y. The acceleration is minus omega square y. Therefore, we have restoring force acting on a particle executing simple harmonic motion is F is equal to, right? Now M is constant, replacing this A will obtain minus M omega square into Y, right? This is the restoring force, right? Acting on a particle executing simple harmonic motion. It is very much simple. When I put this force is 0, F, when the particle is at mean position. This comes into play only when the particle is displaced from its mean position by the action of external force, right? Now when the external force is removed, this force, right, comes into play and brings back the particle to its mean position, right? Is that clear? Now see this equation. Again we have got negative sign here. Now what is the significance of this negative sign here? The significance of negative sign here is that the force is always directed towards the mean position, right? So when the particle overshoots here, say it comes to this position, right? But see here, from here to here speed increases. We know that. For simple harmonic motion, velocity is 0 at extreme position and maximum at mean point. When it starts moving away from the mean position, its velocity goes on decreases. That means the force is acting in the opposite direction of motion. Again here, the force is directed towards the mean position. That is the significance of this negative sign. This negative sign indicates that restoring force always acts towards the mean position irrespective of the position of the particle from the mean position, whether it is in positive side or negative side, right? So positive side means on one side of the mean position, right? The negative side means on the other side of the mean position, right? For horizontal oscillation, positive x-axis, negative x-axis. For vertical oscillation, negative y-axis, positive y-axis, right? So it is clear. So we can come to a conclusion that whatever may be position of a particle executing simple harmonic motion from its mean position, both acceleration and restoring force directed towards the mean position, right? There is no other direction for acceleration and force, only towards the mean position in a simple harmonic motion. Is that clear? So we got it. We will take that equation 2 here, right? This is F is equal to minus M omega square y, where M is mass of the particle and omega is the angular velocity, that is the rate of change of angular displacement, right? Is that clear? Now Now we have, right, restoring force F is equal to minus omega square y, or in vector form it can be taken as vector F is equal to minus omega square vector y. So F and y are always in opposite direction, right? And whenever we are considering magnitude of restoring force, F is equal to, this is minus m omega square y, vector F is equal to minus m omega square y. Now the magnitude of restoring force is m omega square y. We will take this as equation 3. We have already taken equation 1 and equation 2. This is equation 2. F is equal to MEA is equation 1. Right. Now F is equal to m omega square y. Now at mean position, what is the value of y? Here in the right hand side of the equation, m is constant, omega is constant, only variable is displacement. It changes with respect to time. It is at different positions of the particle. So y is equal to 0, right? Therefore at mean position, right, F is equal to 0, and it is the minimum value of force that F is equal to 0, right? Right. Now at extreme position, y is equal to A, therefore the force is maximum and the maximum force is equal to m omega square A, where A is the amplitude of a simple harmonic motion, right? So displacement y, velocity v, acceleration a, and restoring force that we are discussed so far, right? All of them, right, they change with respect to time, right? They are variables in simple harmonic motion, right? Now let us observe that equation. What is velocity v? Velocity v is equal to omega into square root of a square minus y square. Acceleration a is equal to omega square into y. I have neglected the negative sign here. Now force F is equal to m omega square y. We see, or we take y is equal to here a sine omega t plus phi naught. So here y varies with time. Therefore v varies with the displacement time. A also varies with displacement. Force also varies with displacement, right? As this, from these three equations, velocity acceleration and force, they all depend upon displacement of the particle at that instant of time. Therefore, with change in displacement, the values of velocity, acceleration and force are changing. All of them, right, depends upon the displacement, right. Velocity depends upon displacement, acceleration depends upon displacement, and even force depends upon the displacement, right. Is that clear? Here we have negative sign, here we don't have negative sign, because these two are always directed towards the mean position. Such condition is not there for velocity, right. Therefore, it is important to consider, right, displacement, velocity, acceleration and restoring force, both at mean position and extreme position. We take at mean position. At mean position, y is equal to 0, but velocity is maximum. So, acceleration is equal to 0 and force is equal to 0. At extreme positions, y is equal to a plus or minus a, depending upon which side the displacement is maximum, right. Now, v 0 here, when displacement maximum, velocity is 0. A is equal to omega square e, it is maximum. F is equal to ma, m omega square e. These are all the values of displacement, velocity, acceleration and restoring force at mean position and extreme positions of a particle executing simple harmonic motion or oscillation or vibration we can take. Is that clear? Now again, this particle executing simple harmonic motion possesses kinetic energy and potential energy. The sum of kinetic energy and potential energy, right, is equal to total energy, right. These concepts of work and energy we have discussed in the chapter, right, which comes in mechanics. There is a work, power and energy. Again here this kinetic energy and potential energy of a simple harmonic motion is different at different, right, positions, mean position and extreme position, like that, right. That we will discuss later, right. So here angular velocity is constant, amplitude is constant at this stage, but these four, displacement, velocity, acceleration and restoring force, they change with respect to time or with respect to position of the particle executing simple harmonic motion, right. Is that clear? So, it is very important here, right, the equations of velocity, acceleration, force taking different forms, right, at different positions, right, we have taken generally, right. Now, you remember these things. Again, we are using these equations, right, in solving numerical problems as well as, right, problems which will come in competitive examination. The most important thing to solve problems in physics is not only the equations, right. Just by remembering the equations, right, by keeping them in memory, we cannot solve, right, problems in physics, right, because problems in physics are testing the ability of a student, right, the skill of a student, the application of a student, how skillful he can solve the problem, right, how he can able to apply the different concepts. So for that purpose, whenever we are discussing a phenomena, right, whenever we are discussing an event, right, in the nature, we should know what happens there physically without much help of the mathematical equations. And mathematical equation is required because only with the help of mathematical equation we can clearly understand that one. But at the same time, we should know how the things work. That means what is the effect of force, what is the effect of acceleration, what is the effect of velocity on simple harmonic motion, right, or how to set a particle into simple harmonic motion. When we go on understanding what exactly happens in a phenomena or in an event, in an effect, then more easily we can solve a problem, right, in numerical problems. Therefore, right, what my suggestion is, right, along with the mathematical equation or physical expression, one should know, right, the physical things, right, which are happening in an event, in a phenomena or in any other effect, right. Okay, so we have discussed about the restoring force, which is responsible for simple harmonic motion of a particle, right. Okay, students, in this class we have discussed two important concepts: acceleration of simple harmonic motion and restoring force, right. So a force causes motion in a body. So an external unbalanced force is always required to produce motion in a body. And we know that there are three types of motion: translational motion, rotational motion, and oscillation. We call harmonic motion, right. And here, under different conditions, right, the force acting on a body produces translational motion, rotational motion, and the vibrational motion, right? So here, suppose we are having a body on a table, right? A bob, say, I have taken some bigger bob here, a spherical body, right? And now, to move it, right, or we take, because it executes, I am considering a box here, a block, because when I consider a bob or a sphere, it executes two motion. Therefore, we have the concept of particle and the concept of rigid body there, right? Now, whenever a body having mass m, when we apply a force, right, that produces acceleration ma, the body starts moving with acceleration and gains velocity, right? If you throw a ball, right, you are exerting the force, that force produces translational motion. Suppose I am having a sphere, imagine the globe, right, which is always there on the table of a teacher, I mean headmasters, right, generally. How to rotate it? Just you are applying a force, you pull it, right? If you touch it like this, it will fall from the table. How do you apply? You apply like that. You apply the force in a specific manner, right, to produce rotational motion, right? That effect what you are producing on the globe, right, to produce rotational motion, right, is different from this effect, right? And this is called, the effect is called as torque. So, force only does not produce translational, rotational motion. It is torque that produces a rotational motion. So, simply here, to produce oscillation, what you will do, right? You will take, if you apply the stand like this, or you apply it on the string, no, you just, right, pull it aside to make the simple pendulum to oscillate. Then you will apply a force which is displacing. Now why we are displacing that one? Because when the bob is displaced, there comes restoring force, because it is fixed to a point here. You got my point, right? Now here also it is fixed to an axis called axis of rotation, right? Therefore, to produce three types of motion, of course force is required, but the forces are applied in a different manner, right, to produce, right, different motions. Here, any external unbalanced force can produce translational motion. Only a torque can produce, right, rotational motion. And of course, this torque is the product of force and perpendicular distance. We will discuss later. But here, the force is called restoring force, right? So when you spin a top, right, bugri, right, then the force, that is the thing that causes rotational motion, is a torque, right? Therefore, specifically the force in simple harmonic motion, right, that in fact that causes simple harmonic motion is a restoring force. In that way it is necessary. In translational motion it is any general force. In rotational motion only a specific manner of application of force, that is torque. Here also there is a specific manner of applying the force, right? That force is restoring force, right? Now, only the thing is we have to induce a restoring force, right, in the particle, then only it executes a simple harmonic motion, right? Suppose if you remove the suspension, then you move it, the bob. When the same bob without any suspension, it is moved here, it comes to some position here. It will not return back. Why it will not return back? Because there is no restoring force here. There is no restoring force here. When the bob of the simple pendulum, instead of being suspended, placed on the table, right, and it is moved from one position to another position, it will not return to its initial position because there is no restoring force, right? So, the restoring force arises in the bob when it is suspended by a spring or thread to a rigid point, fixed point, then applying the displacement force or external force, right? So, let us conclude this class, that is part number 6. In the next class, that is part number 7, right, we are going to discuss some other important concepts like force constant, number 1. Number 2, right, let us obtain an expression for period of simple harmonic motion in general, right? It is applicable to the particle, any particle executing simple harmonic motion. Condition is that whose acceleration A is equal to minus omega square y, right? And frequency of simple harmonic motion, that is the number of oscillations executed per second, right? Let us find an expression for period of oscillation of a loaded spring. I think in part 3 or part 4, I have shown you the spring, a loaded spring. Of course, it is not oscillated there, I can't show it because that mass of the block I have taken is very, very small, right? It can hardly produce the higher frequency, right? We cannot able to observe that motion, right? So, let us conclude the class at this stage. Thank you very much.